The next experiment is demonstrating the Pockels effect in a conoscopic beam path. The objectives of this experiment are to identify the optical axis of the birefringent crystal of the Pockels cell in a conoscopic beam path. Now, what is birefringence? So, birefringence or double refraction is basically there are some crystals like calcite or quartz. When an ordinary ray is incident on these crystals, the rays are getting refracted into two rays, one of which obeys the laws of refraction, that is Snell's law, which is called ordinary ray or O ray, and the other ray doesn't obey the laws of refraction, that is, it doesn't obey the Snell's law, and it is called the extraordinary ray. So both extraordinary ray and ordinary ray, that is E ray and O ray, both the rays are polarized. This phenomena is called double refraction or birefringence. So it is the property of some materials, optical materials. The refractive index depends on the polarization direction. So in birefringence there are two refracted rays, O rays and E rays. So O rays travel with equal velocity in all directions and obey the ordinary laws of refraction, that is Snell's law. E ray does not obey the laws of refraction, and optical properties of uniaxial crystals are perfectly symmetrical about the optic axis. That is, in along the optic axis, the velocity of the O ray and E ray is similar. Along this axis, optic axis, the velocity is equal and there is no double reflection. For a crystal in which O ray travels with a smaller velocity than the E ray, that is, refractive index of E ray is less than refractive index of O ray, that is NE less than N0, in the direction normal to the optic axis are called negative crystals. Whereas if the crystals in which the velocity of the E rays is smaller than the velocity of O rays, that crystals are called positive crystals. So in this picture we can see that the birefringence in the crystal where two rays are refracted in that crystal, and the other figure is basically the variance of refractive index with respect to wavelength for the extraordinary ray and ordinary ray in alpha quartz crystal. Now, what is electro-optic effect? The electro-optic effect is basically the alternation of the refractive index of a medium when electric field is applied. So in presence of electric field, the variance or the change in refractive index in a crystal is generally considered as the electro-optic effects. So there is two types of electro-optic effects we'll consider. One is Pockels effect and another is Kerr effect. So in Pockels effect, non-centrosymmetric materials exhibit that phenomena, that effect, and it is named after the discovery by Pockels. And the refractive index, the change in refractive index is proportional to the electric field strength, so it is linear with the electric field. And in Kerr effect, all centrosymmetric media exhibit this Kerr effect, and here the refractive index, the change in refractive index is basically proportional to the square of the electric field, so it is quadratic uh, in electric field. So due to electro-optic effect in a isotropic medium, there is an induction of anisotropy, that is an anisotropy nature is induced due to the applied field electric field, and for anisotropic media the polarization, the nature of the polarization get changed due to the electric field. So in both the cases, where it be the isotropic media or anisotropic media, the nature of the polarization, the state of the polarization is getting changed by the electric field, and the refractive index of that materials is getting changed by the applied electric field. So in isotropic media, birefringence is induced, and the materials which actually doesn't show the birefringence, there is induction of birefringence property, and when it is already a birefringent material, the change of polarization, the nature of polarization is getting changed, hence the refractive index of that materials is getting changed under the influence of that field, external field. So there will be a change in permittivity. So the changes in permittivity or the refractive indexes due to that external field, electric field, this is called electro-optic effect. This phenomena is called electro-optic effect. And light can be modulated. The nature of the polarization can be modulated with the suitable configuration or orientation of the media with respect to the propagating electromagnetic waves. So the birefringence, which is which will be which is induced in that material, in this medium, can be electrically controlled externally in their magnitude of the external magnetic field. And in anisotropic medium, the state of polarization can be electrically controlled by that field. So it can be it can act as a light modulator. So refractive index of a electro-optic medium is a function of applied electric field. You can see the picture. A nucleus is there, and around this outer electrons are there in this crystal lattice. So if now we can view the crystal from the two orthogonal positions. So the first picture from the left one, we can see that it is identical. So whether we can see from the left or the lower part or upper part or right or from the right, we will see the same configurations of these systems. But now if the electric field is applied, then we can see that there will be distortions in these configurations, and it will no longer appear same as we see from the different angles, from the different orthogonal positions or directions. So the external electric field creates the anisotropic configurations of this crystal. So this is a simple model of electron clouds or distortions of electron clouds, from where we can understand the basics of the electro-optic effect. Now we'll see the index ellipsoid. So we can see that the in absence of the electric field, the index ellipsoid is a sphere. So nx, ny and nz, it is equal, and it is defined as x square plus y square plus z square is equal to n0 square, where n0 is nx and ny and nz. So for isotropic medium in index ellipsoid, nx, ny, nz is equal, and it is equal to n0. So this equation becomes sphere, and the equation is defined as x square plus y square plus z square is equal to n0 square. Now in presence of the electric field, so it is getting it is not it will not be no longer sphere. So sphere symbolizes the uh, isotropic medium, but when in the electric field is present in that medium, then nx, ny and nz will no longer be same, and the sphere will be distorted to a ellipse. So we can have the general ellipsoid, and the equation is given by x square by nx square plus y square by ny square plus z square by nz square plus 2yz by nyz square plus 2xy zx by nxz zx square plus 2xy by nxy square is equal to 1. So it is nothing but the general ellipsoid. So from this picture we can see that the isotropic property of this medium, so it is getting distorted to an isotropic, and in presence of electric field, the isotropic medium will become the anisotropic. Now move to a case where the medium itself is anisotropic. So suppose a medium can be defined in the as nx, the index ellipsoid as nx is not equal to ny, not equal to nz. Still the ellipsoid is a principal axis system, this ellipsoid. So the equation will be x square by n x square plus y square by n y square plus z square by n z square is equal to 1. So it is ellipse, but it is not the general ellipsoid. So in presence of electric field, this anisotropic medium will also be anisotropic, but the property, the orientations will be different. So it will become a general ellipsoid. So here we can see how the anisotropic medium will be affected. The properties of anisotropy medium will be altered in presence of electric field. Now we'll see how the refractive index of the material and the E ray and O ray of the material can be demonstrated, can be written as a function of E. So we can say Ne, that is refractive index, when as a function of electric field E, is equal to N0 plus dNdE when E is equal to 0 into E plus half into d2n dE2 when E is equal to 0 E square plus, and the series of this Taylor expansion will go on, and ignoring the hiring terms, we can say that it is n0 plus, and this dNd at E is equal to 0, we can write we can say it as a1 so it is n0 plus a1e plus half, and the double derivative with respect to E at E is equal to 0, we can say it as a2. So now Ne becomes N0 plus A1E plus half A2 E square, and we have ignored the further higher terms. So we got delta n is equal to n function of E minus N0 is equal to dn de at E is equal to 0 into E plus half d2n d2 at E is equal to 0 E square. Now delta 1 by n square, we can say that it is minus 2 by n cube into delta n. So here putting the value of delta n, so we get delta 1 by n square is equal to minus 2 by n cube dn de at E is equal to 0 into E minus 1 by n cube d2n d2 at E is equal to 0 E square. So delta 1 by n square, it can be modified as r into E plus s into E square, where r is equal to 2 by n cube dn de at E is equal to 0 and s is equal to minus 1 by n cube d2n d2 at E is equal to 0. So for those materials who, where S term is negligible, we'll have delta 1 by n square is equal to r into E, and delta n is equal to minus half into r n cube into E. Here r is the Pockels coefficient. Okay, so the typical values of r is 10 to the power minus 12 to 10 to the minus 10 m by v, or 1 to 100 pm by v. So this is the Pockels effects formula, and we can see that the delta n, that is the change in refractive index, is linearly proportional to capital E, whereas for the Kerr effect, the change in refractive index will be a function of E square. There if the material is centrosymmetric, so r will be 0 and delta n will be minus half s n cube E square. So delta n here is proportional to quadratic of the electric field. So delta n will vary as E square. So which material will exhibit the Pockels effect? So here in our lab, lithium niobate LiNBO3 will be used, and other than that, KDP, ADP, lithium uh, tantalate can be uh, used as the Pockels effect experiment. And for Kerr effect, the material is nitrobenzene, nitrotoluene, etc. Now, what is centrosymmetric crystal? So, crystals which exhibit inversion symmetry and the Rij coefficients are identically 0, and for inversion symmetry, the direction xyz and minus x minus y minus z are indistinguishable, and all applied field E and minus E must induce the same electro-optic response. So this is the centrosymmetric crystal, and that centrosymmetric crystals will exhibit the Kerr effect, whereas non-centrosymmetric crystals will exhibit the Pockels effect. So this is the electro-optic effect, and we will demonstrate the Pockels effect in our lab. Thank you.